welcome back. This is evading AWS GuardDuty and network firewall using privacy-enhancing tech. So before we start, as always, I'd like to thank our sponsors, especially our bronze sponsor, IAMPulse. Change is constant, change is scary. IAMPulse brings clarity and depth to Terraform pull requests by delivering meaningful insights about what could happen downstream if a change is applied. Join our private beta as a design partner to see it in action, iampulse.com/beta. For those in the room, as always, please silence cell phones. We'll do questions in the room and also on Slack and Twitter. Please welcome Dhruv.
Thank you. Hello, everyone. I am Dhruv. We'll be demonstrating how to craft certain fairly easy to craft packets which can evade GuardDuty and the network firewall. I know this is the last presentation between you and lunch, so I'll try and be very efficient, although it's fairly technical. And so I hope all your pistons are firing today. The services we will cover in this slide deck are Amazon GuardDuty, which I'm sure you're all familiar with, the Route 53 resolver DNS firewall, and the AWS network firewall, which sits at your VPC perimeter, more of an intrusion prevention system. The Amazon GuardDuty, it should be noted that it works off monitoring logs from CloudTrail DNS, which is the Route 53 resolver firewall, Kubernetes control plane, and your VPC flow logs. The heart of the topic is privacy. It's defined as the protection of your autonomy, anonymity, right to association and expression by the Electronic Frontier Foundation. If you are more interested about the topic, you should really look at their surveillance self-defense section on the website. The two particular technologies that we will look at today are encrypted DNS, or a particular flavor of it, which is DNS over HTTPS, and encrypted client hello. These are the two traditional, conventional ways by which your ISPs or certain regimes monitor you, track you. So these standards have evolved to protect citizens from such invasion of privacy. But then, because technology is technology and it works uniformly across all our infrastructure, the same techniques have been used to evade, encrypt, GuardDuty, etc. So let's dive in. GuardDuty in action. This is a curl command that, if you run, will trigger a GuardDuty alert. This is built into some AWS-owned GitHub GuardDuty test that if you hit xmr.pool.minergate.com, it does raise an alert. I won't necessarily cover the curl switches just yet. There are more complicated ones ahead, which is when I'll cover them. And then the GuardDuty alert fires off in about 13 minutes or so. You can see here that it says some EC2 is querying a domain name that is associated with Bitcoin-related activity. This is the lower half of the same screenshot. It has correctly identified that it was a DNS request. Protocol was UDP. And the time is completely accurate. And it also was able to very plainly identify the exact domain name that we queried. It should be noted that GuardDuty has alerted you on that DNS was requested, not that a connection was established. And the threat list this was found in is owned by Amazon and Proofpoint, maybe both of them. This is a relatively new switch, but it was introduced in curl in the year 2018. I have seen this version of curl, or a better version of curl, in all sorts of clouds, all sorts of Linux distros in the last 2 or 3 years anyway. DNS over HTTP URL, in which you are able to specify a URL, not an FQDN or an IP address, to a DNS over HTTPS endpoint. And then curl will avoid calling your operating system resolution path. And look at this curl output. It first connects to Cloudflare's DNS server, connects to 1.1.1.1. It receives a certificate from Cloudflare. Interesting to note that the subject alternative name actually has an IP address in it, as opposed to a host name. And the other few lines that you see are DNS over HTTPS, spec-based HTTP semantics of carrying out a DNS over HTTPS request. This is still curl output. What you see is answer from DNS over HTTPS server, replying with A records, C names, and then curl picks one of them finally, and then connects to its destination. The whole operating system path, VPC resolver path, etc., has been completely bypassed. This is what it looks like in VPC flow logs. Because the connection was fairly outbound to the internet, VPC flow logs were able to capture it. You can see in the first arrow, it was 1111. Second arrow, that port was 443. Last arrow, which is the fourth line, the first number is 6. That means it's TCP. Again, Daniel covered VPC flow logs pretty well in the last presentation. So thank you, Daniel, for that. This is a screenshot from GuardDuty when you do that. There's nothing. I've waited a long time, nothing still. This is the summary of what has happened. The source for the GuardDuty alert was resolver's logs. The resolver is, as you know, at the second IP address of your VPC, which is assigned to your OS by the DHCP settings of your VPC. But you can also hit the resolver at that link local IP. The query never went to it. There was no log line generated. This is the same mechanism by which you can also bypass the Route 53 DNS firewall, which we will look at now. This is how I had set it up. api.okta.com allowed, everything else blocked with an asterisk in that priority order. If you do a NS lookup, dig, or whatever your preferred tool is, you will get an answer back with a CNAME to that. If you looked up something else, like c2.netlify.app, no answers back. Immediate return with no answers back. But if you just sent the query to a different DNS server, you, of course, get an answer back. Nothing exciting here to look at. Of course, you can look at the query flow log again, because the request went to the internet. This was 8888 port 53. And on the second arrow, you see the number 17, which means it's IP protocol UDP. Of course, you can easily prevent this. I'm sure you already have by blocking UDP outbound completely, especially port 53. This is a close-up of how the packet capture looks in Wireshark. The first and the second arrows reflect the IP layer and the UDP layer. The VPC flow logs never enter the payload of TCP or UDP. They remain at the IP or the UDP, TCP, ICMP, etc. layers. Only some fields of the metadata, like Daniel had explained. The actual query or the answer will be in the payload, and the VPC flow logs are never going to go into that level. But the other service, AWS Network Firewall, is an IPS. It will be able to parse packets, which we will look at. On this occasion, we are also launching a DNS over HTTPS IP's threat feed. It is free for you to use. The URL is on our Twitter feed today. I will share that link shortly. But it's scraped from a few sources. It's verified. It's enriched by going into a bit of the DNS infrastructures and adding those IPs back, which I'll show in the next slide. And we have some sort of roadmap on it, which is not really cast in stone, but we will implement a sticks format. This was the most interesting part while we were doing this. Most of the large providers who own vast chunks of IP address spaces on the internet had their IP addresses embedded in the SSL certificates that were listening on these DNS servers. So they were valid to be queried without creating a client-side SSL warning issue by using an IP address. You can't get these certificates from a free service like Let's Encrypt. Most of them were DigiCert. You would rather own the IP addresses if you're going to do this. Some of the ISPs I've spoken to were just bored ISPs with spare kit. Let's do a DOH. When we get to sticks, we will reflect this in some way, shape, or form in that format. So the conclusion from this, or my reading of this, is that these IP addresses are fairly stable. and they can be relied upon. Like, for example, we've used 1111 and 8888 for how many years now? It's a text file. You can load this in GuardDuty, add a threat list. It's in the latest tweet. I will share that information on the last slide as well. Thanks to KDO Security, they discovered Dadonia who were using DNS over HTTPS. Just one minor comment to make on how to improve malware there, that if you were going to use a DNS over HTTPS server and you used the fully qualified domain name of the DNS over HTTPS server, then the first query would have to go through your VPC resolver, which would then detect it. You could rather just use an IP address of a fairly stable, large provider. Of course, this was for educational purposes only, like everything else in this presentation. If you have such a list loaded from us or from anyone else, GuardDuty will fire an alert of any activity to that IP address, whether it's UDP, TCP, whatever port. Normally, I'm not expecting businesses to be talking to DNS over HTTPS servers in their regular operations. We do, because we have to build the list and test it. But unless you are in the business like ours, you should probably not be talking to it. So it should be fairly safe to plug it in. Anyway, it's GuardDuty, so it's not going to drop any packets. Now we move to the network firewall. This was the configuration stance. These domain names are allowed over TLS or HTTPS. These domain names are not random. According to our data, these are some of the most common ones outside any industry or business-specific FQDNs. You have container downloads happening from key.io and docker.something, GitHub, a monitoring service, and an alerting service. This is the usual topology of AWS Network Firewall. It sits after the NAT gateway, which means that all the client IP addresses it sees are of the NAT gateway as opposed to individual workloads. So you just get to see the one exact IP of all the traffic in it, in its logs. This is the network firewall in its normal operation, that you try to reach api.github.com on HTTPS or TLS, and you get a certificate from api.github.com. And in the response, we see that there are some three headers which proclaim to be or look like they are from github.com. This is another test of the network firewall, where you set a timeout of 10 seconds and try to hit c2.netlify.app. The TCP handshake does successfully culminate. That's the TCP three-way handshake. But as soon as, on the second arrow, you'll see a client hello is initiated, which is where the FQDN is specified in the TLS protocol so that the receiving server can send you back the right certificate. This happened after we started running out of IPv4 addresses. The operation has to time out because the network firewall starts dropping packets as soon as it sees that. This is a typical alert log from the network firewall. It says not matching any TLS allow listed FQDNs. TLS SNI was c2.netlify.app. AWS don't hide the fact that it's Suricata running under the hood. So if you really want to look at more details on what TLS fields it can tell you, just go to Suricata. This is how you would evade the network firewall. This has very interesting curl switches. I'll explain connect to first, which is that if curl wants to connect to the thing on the left, actually dial out to the thing on the right. So this one says, for outbound connections to api.github.com port 443, please actually connect to this IP on that port. It's easier than overriding your host file, but it's effectively the same because editing the host file will need root access. It could leave some trail behind. The point here is that any client, any malware, custom-written software can absolutely make any arbitrary TCP connection and send any data on it. It doesn't have to agree with DNS. So in this case, this IP is actually from c2.netlify.apps lookup. We changed the host header as well so that when the connection terminates after TLS and ends up on the local proxy of theirs, it is able to find a local host with that name. And we add the insecure flag because the certificate it will now receive is not going to match api.github.com. And we will see the packet capture of this from Wireshark now. In the first line, you see that the IP is the one we specified. But deep down in the payload, deep down inside the TLS handshake, the server name extension is set to a server name value of api.github.com. And there we go. It has been able to connect. It receives a certificate from Netlify. The headers also confirm that. You could raise an objection to say that how do you get the IP address in the first place? But you can also get an IP address in the first place by using the exact same technique that you connect to. You say that you're connecting to api.github.com, but the part in red is the HTTP parts of it, which is the path and the query. But in fact, you send it to 8888 and change the host header to 8888 as well. So 8888 receives it and thinks, OK, yeah, it's the resolve path and the expected query, so let me give them an answer. You get an answer. If you were a script kiddie, you could do a subshell out of it. You could write custom malware, whatever you prefer. AWS also have declared this in their documentation that it does not actually do any DNS checks. If you want to inspect these situations, then you will have to write separate rules for that. My guess is they want us to use IP addresses, but if we had IP addresses, it would be a very different story. In the future, there's a new standard being developed. It's not RFC yet. It's still in draft. It's called TLS Encrypted Client Hello. It used to be called Encrypted SNI, server name indication. The TLS server name indication that you have seen before in the Wireshark packet captures will remain as it is. It will be called outer client hello with the specific purpose of showing it to any censorship firewalls or the Great Firewall. There will be an inner client hello extension, which will have encrypted information on what you want to connect to. And it's moved on from SNI to ECH because things like even the application layer protocol negotiation has also become encrypted or will become encrypted. Curl is ready to implement this when it becomes RFC. And Firefox already does it. Cloudflare already do it. There's other websites which are already doing it. Fastly and Cloudflare are the major players behind this draft. This is what it looks like. This is an actual Firefox run behind an AWS network firewall. You see that the server name indication is set to cover.defo.io. I'll talk about defo.io in a second. And then right at the bottom, there's an unknown extension type, 65037, with some gibberish in it, encrypted data. 65037 is what the decimal representation of that ECH drafts encrypted client hello hexadecimal looks like, what they have tried to reserve. It's a bit annoying because they've changed this number about 9 or 10 times, so it's a bit of a work to keep up. Every time they get a new draft, they get a new number. No affiliation with defo.io, but that's the place to go if you want to play with it. They will tell you how to configure Firefox for it, how to compile curl, OpenSSL, etc. for it. And you can also run a test against one of their landing pages, that your outer SNI was different from the inner SNI. Pretty much the last slide. What can we do? Always read the documentation, go beyond the blog posts and the marketing copy. The good vendors always tell you what they are doing and whatnot, and the documentation may have been written by the engineers, so they will come clean. Get involved in the IETF. The next one is in Philadelphia next week, and then in London in November. Go into the TLS working group and as security, tell them your concerns that this is taking away too much visibility in the name of privacy. And if you actually read that draft, I think it burns too much energy to get away with what they want to do in the name of privacy. It's not carbon efficient, you could say. Microsegmentation is very important. Don't share your allow lists in any system which are to do with the build time with runtime. And also check for ethical alignment, whether if you've been asked to protect a piece of infrastructure, was it preventing humans from doing something, or was it keeping machines in order? Because privacy is a thing we should allow for ourselves, but maybe not in a corporate environment, or maybe not from service to service communication. And use our IP addresses list for DNS over HTTPS servers. That's where you can find the tweet at my company's handle. And you can also follow me for more work on network security related research. Thank you.
Thanks. So I guess the first question is, have we yet seen examples of this being abused by malware families, or is it still maybe a little bit off?
No, we have. Like Caddo Security had discovered, Denonia was using it already.
Cool. Yeah, so I guess you I think covered this pretty well, which is, other than allow listing, we kind of expect to see more of this. Are there other other strategies for anomaly detection or other sort of metric hunting that you think would cause this sort of activity to pop out?
Not in my mind. I can't think of anything on that.
Cool. Any other questions from the room? Sure.
Have you looked into whether other commercial firewalls have behaved in this scenario?
Yeah, so the NGFW class don't. They are fairly up to date and capable. My own company built a firewall which is not doesn't suffer from this. The AWS network firewall is actually an IPS. They should have called it an IPS. That's what Google did when they launched their service. But yeah, if you invest in a proxy which will terminate a connection and then forward it, or if you invest in a very expensive firewall, it will be okay.
Yeah, so you said something intriguing at the end about having different technologies for blocking computers versus blocking humans or surveilling humans. Do you think that we should also have different protocols for these two, where maybe we have one protocol for computers that can allow enterprise-grade inspection, and then maybe another one for humans, and then maybe our enterprise proxies and such can then switch to the latter for leaving the perimeter?
That's a very good question. I think we should, but the answer may already lie in Google's PSP protocol, which has a configurable level of encryption, that which fields do you want to encrypt, which you don't. I haven't actually played with it yet, but that seems the right use case for the right sort of design for balancing between observability, logging, and privacy. So you can adjust which fields you want to encrypt and which you don't want to encrypt. It's not as fixed in nature as TLS. But yeah, it might as well be a different protocol.
All right. Quick announcement before we end. We're going to take lunch break next. So lunch should be set up in the pod 3 room out there. Feel free to pick something up. You can eat outside. If indoors is a little bit crowded, mask policy and all that, you can leave right through these doors or go out front or whatever. We will be starting back up in an hour. Thank you, Dhruv.
Welcome.